So what we are going to be talking about today is the concept of Thevenin and Norton equivalent circuits. And we're going to start with Thevenin equivalent circuits. All right, so Thevenin's theorem. Thevenin's theorem states that any linear electrical two-terminal network can be replaced at the terminals by an equivalent voltage source VTH, I'm going to underline that, in series with an equivalent resistance. RTH. All right, so effectively, all this statement really says, or all this theorem really says, is that if we have a two-terminal linear network, we can replace it with a practical voltage source that is electrically equivalent, which we actually did that a little bit on Monday's lecture, okay? But the rules for the equivalent voltage source here are a bit more clear, okay? So we're gonna replace it with a practical voltage source having a voltage VTH in series with a Thevenin equivalent resistance RTH. Well, the equivalent voltage VTH is the open circuit voltage measured at the terminals of the live network, where a live network simply means that all of the independent sources are on. And our Thevenin equivalent resistance, RTH, is the resistance seen looking into the terminals of the dead network, where a dead network is simply one in which all of the independent sources are turned off. So we are going to look at the following circuit and use it as a means to develop our general process. All right, so this is our network. Okay. So what we are about to do is we are going to find the Thevenin equivalent circuit with respect to the 1 ohm resistor. Okay. So effectively, we are going to find the equivalent circuit of what is connected to the 1 ohm resistor, which means the 1 ohm resistor in this case is playing the role of the load resistor like we had in the circuits that we analyzed on Monday, okay? So find VTH and RTH with respect to the 1 ohm resistor, okay? So if we're going to use the Thevenin equivalent circuit method, we need to make this a 2-terminal network, okay? We are going to do that by removing the 1 ohm resistor. Okay. So if I'm finding the Thevenin equivalent circuit with respect to a particular circuit element, I take that circuit element out, meaning that I replace it with an open circuit. Here's 10, 5, 10, and another 10, okay? So whenever I'm trying to find the Thevenin equivalent circuit with respect to an element, I take the element out of the circuit, giving myself a 2-terminal network, okay? To calculate our Thevenin equivalent voltage, that is simply the open circuit voltage. So V Thevenin is nothing more than the voltage drop that we observe across that open circuit set of terminals. So how can we go about finding this open circuit voltage? The short answer is any way we see fit, okay? So how would you guys like to analyze this circuit to determine the quantity VTH? Michael, you have a suggestion? Mesh, okay? Seems reasonable. So if we're going to apply mesh analysis, I'm going to identify my mesh currents Why don't I put a mesh current in the bottom right-hand corner? Because there's an open circuit there that's going to force that mesh current to be 0, which is effectively what you guys all said. Okay. So there are only 2 meshes. There are no current sources or anything like that, right? So we don't have to worry about any super meshes. So we've identified and labeled our meshes. We don't have any dependent sources, so we have no controlling variable relationships to define. We don't have any current sources, so we don't have any current relationships to define. So we are already up to the stage where we write our KVL equations. Everybody okay with that? So let's write our KVL equations. So KVL around mesh A is going to look like -4 volts plus 9 ohms times IA minus IB plus 3 volts is equal to 0. And KVL around mesh B is going to look like 9 ohms times IB minus IA plus 10 plus 5 plus 10. So I'm just going to call that 25 ohms times IB is equal to 0. Or I just lumped the 10 ohm resistor in the top right, the 5 ohm resistor, and the 10 ohm resistor in the middle right, all together into a single resistance because they're all in series. Okay. So I have a simple 2-equation, 2 unknown system. So let's take a moment and solve this for IA and IB. So my coefficient for IA in my first equation is 9. My coefficient for IB in my second equation is -9. And then my constant term is going to be 4 minus 3 is 1. In my second equation, my coefficient for IA is -9. My coefficient for IB is 9 plus 25. And I don't have a constant term. Solve, and I find that IA is 34 over 225 amps, and IB is 1 over 25 amps. Anybody else get that result? Great. All right, so now that we know those two mesh currents, how do we solve for the quantity VTH? So that's going to be part of it for sure. So what we're going to do is we're going to do Kirchhoff's voltage law around that bottom right-hand loop. But we're going to do it in a very specific way. So I'm going to say that this is a voltage V10. Actually, I'm not going to call it V10. I'm going to call it VX because that's going to be confusing. And this is a voltage VY, like so. And I've chosen these polarities explicitly because they will allow me to write VTH, my open circuit voltage, is VX plus 3 volts plus VY. Everybody okay with that? So with the polarities indicated, the potential difference between this node and this node is VTH for the right-hand path and VX plus 3 volts plus VY for that left-hand path. Okay? So Kevin, I believe it was suggested that the voltage drop over that top 10 ohm resistor is simply 10 times IB. I agree with that wholeheartedly. What's the voltage drop? VY. So the voltage drop over the bottom 10 ohm resistor. Exactly correct. The voltage drop over the bottom 10 ohm resistor ZY has to be 0 volts because there is no current flowing through it. And Ohm's law tells us that if I is 0, V is 0. So from this, I get a voltage VTH of 17 over 5 volts, which is the same as 3.4 volts. So this is my Thevenin equivalent voltage as seen by the 1 ohm resistor. If I had pulled any other resistor out, my Thevenin equivalent voltage would be different, okay? So it matters where we're measuring it from. All right, so to recap what we did here, just very briefly, since we're finding the Thevenin equivalent with respect to the 1 ohm resistor, we pulled the 1 ohm resistor out of the circuit, leaving behind an open circuit pair of terminals, and then we measured the voltage drop over that open circuit pair of terminals, giving us our Thevenin voltage. All right, now let's talk about our Thevenin resistance. Yes, sir. No. So it is simply the value of the equivalent voltage source that will appear in the Thevenin equivalent circuit. And we'll talk about what that means in a moment, okay? Right, so that is not going to be the voltage drop over the 1 ohm resistor. In fact, if the 1 ohm resistor were there, I bet it would be different. I practically guarantee that it would be different. All right, so we've got our Thevenin equivalent voltage. Now we're going to find our Thevenin equivalent resistance. And I'm going to walk us through the steps that entails. So I'm going to redraw my circuit with my 1 ohm resistor removed. And 10, 10, 4, 9, and 5. Okay. So to find the Thevenin equivalent resistance, we look in through the open circuit terminals, but we need to be looking at a dead network. A dead network means that all of our independent sources are turned off. Does this circuit, as it's currently drawn, contain any independent sources? Yes, both of those voltage sources are independent. How do I turn off an independent voltage source? Replace it with a short circuit. Absolutely right. So I'm going to short out my 4-volt source and short out my 3-volt source. And at this point, we have a simple resistor combination problem, right? So I'm going to identify my nodes. So here's one. Here's another. Here we have a 3rd node. And here we have a 4th node. And for the sake of argument, I'm going to label them. So I'm going to call this one A, this one B, this one C, and this one D. And the resistance seen between A and B is my Thevenin equivalent resistance, right? So for me to get from A to B, I obviously have to go from A to D to B, or from A to C to D to B, right? There's no way, so let's start with the most simple observation. There's absolutely no way that I can get from A to B without going through node D, right? Because node D is the only one that's connected to node B through that 10 ohm resistor. So I'm going to put D here. There's my 10 ohm resistor. and I'm going to check mark by it because that's the one that I used. I can go directly from A to D through this 10 ohm resistor. Or I can go from A to D passing through node C. So from A to C is my 5 ohm resistor. From C to D is my top right 10 ohm resistor. And I've taken into account this guy and this guy. Why isn't my 9 ohm resistor going to show up? It's shorted out. Since it's touching the same node on both sides, it's going to contribute nothing to our equivalent resistance. All right. So what's 10 in parallel with 15? Oh, you guys shouldn't need your calculator. It's 6. 150 over 25 is a pretty easy thing to do in your head. So 6 in series with 10 is 16. So our Thevenin equivalent resistance here is 16 ohms. Are we okay with that? All right, so let's put these two things together. I'm going to redraw our original circuit here. And I'm going to draw the Thevenin equivalent. So from the perspective of the 1 ohm resistor, this circuit, same as this. Okay. So 3.4 volt source in series with a 16 ohm resistor is electrically equivalent to that big ugly thing on the left. All right. This would make performing a power calculation or something like that pretty simple. Okay. Now in this class where we're using, nodal analysis and mesh analysis and all that kind of good stuff, we could obviously just use that to calculate, say, the voltage drop across the 1 ohm resistor with it connected to that big network, or the current flowing through that 1 ohm resistor connected to that large network, and then get the power from there. Thevenin equivalent circuits really shine when you're analyzing a massive circuit in a application, to where instead of saying, oh, well, all of these things work together to do this thing, telling me, the power delivered to this particular load resistor. No, you just look at the Thevenin equivalent instead, which you can physically measure rather easily. Because measuring a Thevenin equivalent circuit is simply taking the load out, measuring the open circuit voltage with a multimeter, and then taking the load out, turning the circuit off, and measuring the Thevenin the Thevenin resistance, right? That's what we're going to do in Friday's lab. We're going to actually measure Thevenin equivalent circuits, which is a great way to simplify your analysis to determine, making sure that your resistor isn't going to be absorbing too much power or anything like that that would cause it to burn out. It can be a useful circuit analysis tool as well. All right. So the next thing we're going to talk about here is the Norton equivalent circuit. And what goes into a Norton equivalent circuit is defined by Norton's theorem. Norton's theorem is incredibly similar to Thevenin's theorem, even though they were developed roughly 80 years apart, okay? Thevenin's theorem came first. Norton's theorem was developed by an engineer for, I believe it was Bell Labs, or what we now commonly call AT&T, in the mid-1900s. Norton's theorem says any linear electrical two-terminal network can be replaced at the terminals by an equivalent current source I Norton in parallel with an equivalent resistance R Norton. So effectively, Norton's theorem says I can replace any linear electrical network with a practical current source. I Norton is the short circuit current measured through the short-circuited terminals of the live network and R Norton is the resistance seen looking into the terminals of the dead network. Literally the exact same thing as the Thevenin resistance. Okay. So from here on out, you'll probably never hear me talk about the Norton resistance again. I'm going to refer to the Norton equivalent resistance as the Thevenin equivalent resistance, because they are literally the exact same quantity representing the exact same thing. All right, so let's take a look at that circuit again. our original circuit was this guy. So if we're trying to find the Norton equivalent, we again have to take that 1 ohm resistor out. Okay, so our goal here on the Norton equivalent circuit with respect to the 1 ohm resistor. Okay. So I'm going to redraw my circuit with that 1 ohm resistor taken out. Like so, where this is 9, and sorry, this bottom one here should have been a 10 ohm, not a 1 ohm. It's my mistake. All right, so the Norton equivalent current is the short circuit current, which means we simply short out our terminals and then measure the current flowing through that short circuit. So what analysis method would you guys like to use to determine this current? Mesh, okay. So let's call this mesh current IA. This mesh current IB. And this mesh current IC. We have identified and labeled our 3 meshes. There are no dependent sources, so we don't have a controlling variable relationship to write. There are no current sources, so we don't have any current relationships to write. So we are ready to write our KVL equations. So KVL at mesh A is going to look like -4 volts plus 9 ohms times IA minus IB equal to 0. Literally the exact same KVL equation for mesh A that we had earlier. KVL, oh, sorry, thank you. Plus 3 volts, thank you so much. KVL at mesh B is going to be 9 ohms times IB minus IA plus 15 ohms times IB plus 10 ohms times IB minus IC is equal to 0. And lastly, KVL at mesh C looks like -3 volts plus 10 ohms IC minus IB plus 10 ohms IC is equal to 0. I have a 3-equation, 3 unknown system. So I'm going to throw this into the calculator and solve for IA, IB, and IC. So in my first equation, my coefficient for IA is +9. My coefficient for IB is -9. My coefficient for IC is 0. And my constant term, when I move it to the right-hand side of the equal sign, is going to look like 4 minus 3 is 1. For my second equation, my coefficient for IA is -9. My coefficient for IB is 9 plus 15 plus 10. And my coefficient for IC is -10. Constant term of 0. In my third equation, my coefficient for IA is 0. My coefficient for IB is -10. And my coefficient for IC is 10 plus 10. And when I move 3 volts to the right-hand side of the equal sign, my constant term is then 3. Solving, I get a current IA of 17/72 amps. IB is 1/8 of an amp. And IC is 17/80ths of an amp. Did anybody else get those results? Okay, so what is my Norton current? IC. Fantastic question. Okay. So because my Thevenin voltage was taken with positive polarity on the top, my Norton current would be flowing into that positive polarity term. Now, on your exams and things like that, I explicitly specify the polarity of the Thevenin voltage and the direction of the Norton current. On some of your homework problems, it isn't explicitly stated. On some it is, and on some it isn't for whatever reason. But typically speaking, so let's say if your positive polarity of your Thevenin voltage is on top, then your Norton current should be pointed down. And let's say if your Thevenin voltage positive polarity was on the right, then your Norton current should be directed to the left. Yeah. But in the problems that I write, I try to explicitly tell you which one. The only thing that that's really going to do is wind up giving you a negative resistance, which seems scary, but actually isn't really all that big of a thing. All a negative resistance means is that as you increase the voltage, the current decreases, or as you increase the magnitude of the voltage, yeah, the current gets more negative. So anyway, all right, so our Norton current is 17/80ths, excuse me, of an amp. And so that means that our original circuit, which I'm getting tired of redrawing, so I'm not going to redraw it this time, has a Norton equivalent circuit that looks like this, where the 16 ohms of resistance is the Thevenin resistance that we measured earlier, because Thevenin resistance and Norton resistance represent the same quantity. Okay. So our original circuit has the following 2 equivalent circuits. On the left, we have our Thevenin equivalent circuit. On the right, we have our Norton equivalent circuit. And since these are both equivalent to our original circuit, they have to be electrically equivalent to each other. Well, as it turns out, it shouldn't be too large of a stretch here. The Norton equivalent circuit is just the source transformation of the Thevenin equivalent and vice versa. And we can verify that very easily, right? So we should be able to see that V Thevenin is simply I Norton times R Thevenin, or alternatively, we could see that I Norton is V Thevenin over R Thevenin, or we could see that R Thevenin is simply V Thevenin over I Norton. Meaning technically, if we know any two of these three quantities, we immediately know the third quantity. So we can use that to either shorten our analysis time or calculate all three things and then verify that our calculations are correct by making sure that these relationships hold. So V Thevenin we found to be 3.4 volts. If we divide that by our Norton current of 17 over 80, we get 16 ohms, which means our analysis must have been correct. Yes, sir.
So for the outer resistance,
Absolutely. We can do it with respect to any. Yeah. No, we can find the Thevenin equivalent and Norton equivalent circuit with respect to any element. Michael.
Could you use these circuits to find the voltage drop over 1 ohm?
Absolutely. Yes. So if we wanted the voltage drop over the 1 ohm resistor, we could just do voltage division for the left-hand circuit, or we could use Ohm's law for the right-hand circuit. Sure, why not? And the voltage drop, so let's just be explicit here. Let's call this VL, this IL, this VL, this IL. Obviously, VL has to be the same, IL has to be the same, and if we were to look at our original circuit, the values of VL and IL that we calculate using our Thevenin equivalent are the exact same as that we would observe in the full circuit. They have to be, or they're not electrically equivalent. All right, let's work one more example problem. And then I'm going to be done talking for the day. So this circuit is going to illustrate the other means by which we can define a Thevenin and Norton equivalent circuit, okay? It is not going to take a particularly large change in our approach whatsoever. So here's our circuit of interest. And we are going to find the Thevenin equivalent with respect to the pair of terminals that are given, okay? So sometimes we're not going to be asked to find it with respect to a particular element, but with respect to a set of terminals, okay? And in this case, our terminals are given. So we don't have to take anything out to measure our open circuit voltage because we already have an open circuit. And for our short circuit or Norton current, we will simply short that pair of terminals and then measure that short circuit current. Okay? So our goal here is to calculate the Thevenin equivalent voltage, the Norton equivalent current, and the Thevenin equivalent resistance. Which of those three quantities do you guys want to do first? The resistance, okay. That's fairly straightforward. So for our Thevenin equivalent resistance, we are going to look into the open circuit terminals of our dead network. So Kevin, how do I turn off my 3-volt source? Short circuit, all right. So short circuit for my 3-volt source. Here is my 2 kilo ohm resistor. Kevin, what do I do for my 7 milliamp? Exactly right, open circuit. I look in here. There is RTH, and this should be pretty easy to do by inspection, right? So I see that the 2 kilo ohm resistor and the 5 kilo ohm resistor are in parallel, which is going to look like 10/7 of a kilo ohm. And then I have a 1 kilo ohm resistor in series with that. So 10/7 plus 7/7 is 17/7. And I'm done. Anybody have any problem with the math we did there? All right, somebody else tell me what we should analyze next, the Thevenin equivalent voltage or the Norton equivalent current. Voltage, okay? So for our Thevenin equivalent voltage, we're just going to have our original circuit. And we are simply going to measure this open circuit voltage VTH. Instead of asking you guys how you'd like to do this, I'm going to tell you that we're doing it using nodal analysis, and I'm going to explain the reason why. Here explicitly, what's the voltage drop over the 1 kilo ohm resistor? 0, because there's no current flowing through it, which means the Thevenin voltage is the voltage drop directly over the 5 kilo ohm resistor. Are we okay with that? Okay. Now, if I observe that if I make that terminal ground, the only voltage I don't know is the one at that node, where that nodal voltage is actually my Thevenin equivalent voltage. So if I apply Kirchhoff's current law at that node, I have VTH minus 3 volts divided by 2 kilo ohms plus 7 milliamps plus VTH divided by 5 kilo ohms equal to 0. That's a one equation, one unknown thing that I can solve for VTH directly. I'm going to throw that into my numerical solver. And I get VTH is equal to negative 7.857 volts. Lastly, obviously, we are going to solve for our Norton current. Which will be analyzing this circuit for this quantity I Norton, where I've simply shorted out the terminals and I'm measuring the current through that short circuit. So we'll analyze this one with mesh. Typically speaking, if possible, I usually try to find the Thevenin equivalent voltage with nodal analysis, because if I'm looking for a voltage, I might as well use the method that gives me voltages. And whenever I'm trying to find the Norton equivalent circuit, I use mesh because I'm going to use the method that gives me currents when I'm looking for a current. It's not a hard and fast rule, obviously. Sometimes it may be much more simple to do it a different way, but typically speaking, that's how I approach these. So let's identify our meshes. IA, IB, and IC. We do have a current source, so we have to write a current source relationship. What's that going to be? IA minus IB is equal to 7 milliamps. All right. And now I'm going to need to come up with two Kirchhoff's voltage law equations. So KVL at supermesh AB is going to look like negative 3 volts plus 2 kilo ohms IA plus 5 kilo ohms IB minus IC is equal to 0. And KVL at mesh C is going to be 5 kilo ohms times IC minus IB plus 1 kilo ohm times IC is equal to 0. Okay. Now we can solve this system, 3 equations, 3 unknowns. Actually, before we do this real quick, I just want to point something out. What if we had decided to use nodal analysis here like we did in the last bit? Our unknown voltage, our only unknown voltage, would still be this guy, and our Norton current would simply be the voltage at that node divided by 1 kilo ohm. So we'd have a 1 equation, 1 unknown system and then one additional step to get our Norton current. So think about relationships like that before defaulting to nodal and mesh all the time. All right. Anyway, so let's solve this 3-equation, 3-unknown system. So let's see, in my first equation, my coefficient for IA is 1, my coefficient for IB is -1, my coefficient for IC is 0, and my constant term is 0.007. For equation 2, my coefficient for IA is 2,000, my coefficient for IB is 5,000, my coefficient for IC is -5,000, and my constant term is +3. And lastly, in equation 3, my coefficient for IA is 0, my coefficient for IB is -5,000, my coefficient for IB is 6,000, my constant term is 0, and solving, I get IA is 3.118 milliamps. IB is -3.882 milliamps. And IC is -3.235 milliamps. And we can easily check to see if we've made a mistake. So -7.857 divided by -3.235 times 10 to the minus, 10 to the -3 gives me 2.428 ohms. Excuse me, 2,428 ohms. 17/7 is 2,428 ohms. So we did all of our analysis correct. All right, so I believe that is enough out of me for today. You have an in-class assignment that involves doing this stuff multiple times, so have at it, and I will happily answer any questions that you may have.